Good morning, everybody, and welcome to our last set of notes for the semester. We are looking at the chi-square distribution, and then we're going to follow this up with the chi-square goodness of fit test. So the chi-square distribution is another table that we will use similar to the T table. We've looked at the Z tables, the T tables. We looked at the F table, and now we're looking at the chi-square table. And as I said, the chi-square table is very similar to the T table in how you find the values. The chi-square curve, again, is a right-skewed curve. You can see from the graph there in the middle of the screen that the larger the degrees of freedom become for the chi-square table, that the curve resembles more of a normal curve as the degrees of freedom get larger. Just like all the other curves that we've looked at, the total area under the curve is equal to 1. This curve, similar to the F curve, it does start at 0 and extends indefinitely to the right. So that's why it is a right skewed test. And then the number of degrees of freedom, like I said, as it becomes larger, the curve looks more and more like a normal curve. So using the table, with this being a right-tailed table, we're going to find the degrees of freedom, then we'll find the corresponding significance level, and then we find that value that has the specified attributes. So here we're looking at example 1, and this is the only example for 5.1. That's why we're just going to do two sets of notes together. We have 12 degrees of freedom. Find chi-squared with a significance level of 0.025. So we will go to the chi-squared table. Let's see, 12 and 0.025. And you'll notice on the first page of the table, we have the degrees of freedom down the left-hand side, and the chi-squared alpha values are here across the top. None of those correspond to what we're looking for, so we'll scroll down to the second page. This table is only 2 pages long. So we find 12 on the degrees of freedom, and then we roll over here to 0.025, and we find... Oh, that highlighter's too thick. 23.337. So the chi-square value that has the area of 0.025 to its right is going to be 23.337. And when we look back at our notes, we see that is exactly what we found. Right here is 23.337 in both cases. So that's how you use that table. You find the degrees of freedom, find your significance level, just like we did with the T table, and then you find that associated value. So that's going to lead us into our second set of notes for the day, where we're actually going to apply this to a hypothesis test. And this hypothesis test is called the chi-square goodness of fit test. And this is where we're taking two sets of data that may be separated by, say, years, and we want to compare those two sets based upon whether or not the new frequency of the data is similar to the old frequency, or if there has been a change. And one of the primary functions is in crime statistics. That's where you see this a lot, where you see it used mostly. And so right here with example 1, we're talking about the FBI compiling data on different crimes, specifically violent crimes, and they classify these violent crimes as murder, forcible rape, robbery, and aggravated assault. And the table that we're looking at right now, this table 1, gives the relative frequency distribution of crimes in 2010. So what this is showing, for murder, the relative frequency was 1.2%. For forcible rape, it was 6.8%, robbery 29.5%, and aggravated assault 62.5%. And we have a simple random sample of 500 violent crime reports from last year that yielded the following frequency distribution. We had 3 murders, 36 forcible rapes, 170 robberies, and 291 aggravated assaults, for a total of 500 samples. And what we want to determine is whether or not last year's data indicates the same distribution or approximately the same distribution as what we found in 2010, or if we've noticed that this is going up or perhaps going down. So the first part of this is to formulate the problem statistically by posing a hypothesis test. These are the same steps that we've taken in the past, so this isn't anything new. For this one, we're going to look at our null hypothesis is going to be that last year's crime distribution. So I'm just going to put last year is the same as 2010. And then for our alternative hypothesis, it's just going to simply be that it is different than 2010. So we're going to say that last year is different from 2010. So this is kind of the idea of what our hypothesis test will look like. And with the basic idea for carrying out this test, what we're looking at is the expected frequencies compared to the observed frequencies. If the observed and expected frequencies do match up fairly well, then we're not going to reject the null hypothesis, and that's where our chi-squared value is going to come into play. If they do differ enough, then our chi-squared value is going to indicate to us that we need to reject the null hypothesis. So, discussing the details for making a decision concerning the hypothesis test, there's a couple of things that we have to come up with. We need to look at the frequencies that we should expect from the random sample compared to 2010. So in 2010, we had the relative frequency distribution. We had the percentages of violent crimes. And last year, we have a sample of 500 violent crimes that they've pulled, and we have an observed value. So what we want to look at is, out of those 500 samples compared to the relative frequencies from the year or from 2010, what would we have expected those values to be if they are the same? And the way we do that is we just simply take the relative frequency values and multiply them by, in this case, 500, because that's the size of our sample, and that gives us all of our values for the relative frequency or the expected frequency distribution. And I've done this with a Google Sheet to try to make things as simple as possible. So this first column, column B, these are our observed frequencies. We observed 3 murders, 36 rapes, 170 robberies, and 291 assaults. And that was from the sample data. So what we want to do is we want to have one more value down here in this bottom row, where we're just going to have equals the sum of the values in this column. And that gives us 500. Excuse me. In the second column here, in column C, I have the relative frequency distribution from 2010. That data was given. So what we're going to do is use these values to generate our expected frequencies. And our expected frequencies are very easy. We're just going to simply type in equals, and it's going to be the relative frequency times total of our samples. Now, I've shown you guys this before. What we want to do is take every single value in column C and multiply it by that 500. So in order to make sure that we hold that value in place, we're going to put a $ between the B and the 6. So that way, if you want to just simply drag this formula down, you can, and the Google Sheet will compute all of these values for you. So we can drag this down now, and you can see we get all of these expected values, or expected frequencies: 6 murders, 34 rapes, 147.5 robberies, so maybe 148, and then 312.5 assaults. And what we're doing is we're comparing column B to column D using the chi-squared test. And the chi-squared test to calculate these values, again, is just something very straightforward. What we'll do is we're going to type in equals, parentheses, we want to take our expected frequency, our observed frequency, minus our expected frequency, close that quantity, square it, and then we're going to divide that total by the expected frequency. Hit enter, we get 1.5. We can drag this value down, and then in this yellow box that I've highlighted here, I just put that there because this is where our chi-squared value will go. We're going to total up all the values here under chi-square, and we get 6.529. So that is our chi-squared value that we're going to use for our hypothesis test. So that's the general idea behind conducting a chi-square goodness of fit test. And then what we're going to do in the next example is actually complete that test. So here we have just a couple of notes before we go into completing the test. The expected frequency is the sample size times the relative frequency. That's what we've done in that table. That's why I use that table. It's a lot easier to do that using Google Sheets than it is to do all these by hand. And then you have the distribution for the test statistic. Chi-squared is equal to the sum of the observed value minus the expected value quantity squared divided by the expected values. That's what we did in that last column on the Google Sheet. And then here is the rundown of how the chi-square goodness of fit test is conducted. We have these assumptions. All expected frequencies are 1 or greater. At most, 20% of the expected frequencies are less than 5. And we have a simple random sample. The hypotheses are the null hypothesis, the variable has the specified distribution. The alternative is that the variable does not have the specified distribution. So like we were looking at with the violent crimes, our null hypothesis was that the frequencies were the same from 2010 to last year. The alternative hypothesis is that the frequencies are not the same. Then we compute the test statistic, and then we have our critical value approach and our p-value approach. And again, these are both going to be going back to using the table, and that's what we're going to do with example 2. So we have our data provided here again, and we're just going to refer back to our Google Sheet. Just one more time, we're going to look at what the chi-squared value was. It is 6.529, and that's all we need from that table to complete this test. So we have chi-squared is 6.529. So for our critical value approach, we're going to look at critical value over here. What we need to know is our alpha value, which is 0.05. We know our chi-squared value is 6.529, and we need to determine our degrees of freedom. For a chi-squared test, the degrees of freedom are the number of types or attributes that you're looking at. So in our case, we have murder, forcible rape, robbery, and aggravated assault. So we have 4 types of crime. So we have a C value is 4, and then we use our degrees of freedom, which is going to be C minus 1. So we get 4 minus 1 is equal to 3. So we have 3 degrees of freedom. We have alpha of 0.05, and we have chi-squared of 6.529. So we are going to go to our chi-squared table. We're going to find chi-squared of 0.05. This is the value that we are looking for. There's our alpha value with 3 degrees of freedom. Let's go to the table, and we have degrees of freedom 3, 0.05, and we get that that value is 7.815. So if we imagine this on a curve, remember the chi-square is a right tail curve, 7.815 is here, and it's a right tail test, so it's everything that lies to the right. Our chi-squared value is 6.529, and it lies in the non-rejection region. So for this particular critical value test, we do not reject the null hypothesis. When we look at the p-value approach, we know that we have degrees of freedom of 3 again, and we have a chi-squared value of 6.529. So what we want to do is go to the chi-squared table. Again, we're focused on the 3 degrees of freedom, and we're trying to find where does our value of 6.529 fall in this particular table. 6.529 falls between these two values, so we get a p-value of somewhere between 0.05 and 0.1. So once again, we go back to our notes here, and we know from the chi-squared table that our p-value is between 0.05 and 0.10. With the p-value approach, anytime your p-value is greater than your significance level, you do not reject the null hypothesis. When it's less than your significance level, you do reject. Our significance level also happens to correspond to 0.05. And we can see from what we've written here that p is certainly greater than 0.05. It actually is somewhere between 0.05 and 0.1. So we do know that p is greater than 0.05. So we do not reject the null hypothesis. And that is that's how you conduct the chi-square goodness of fit test. There's several problems on here. What I'd like for you guys to do is we're not going to do anything from 5.1. I'm just going to give you 2 problems from 5.2 to get you some practice, because the final is going to only be 4.1 through 5.2. So let's do question number 1 and then question number 3. So question 1, question 3, and that will be due. We'll make these 2 questions due Friday, same day as the final. They must be submitted prior to the final, so they have to be submitted before noon on Friday. The final will be noon to 2, and we are still going to try to work out a Zoom schedule for hopefully tonight if possible, but we'll work that out, see what time that I get home this evening. I hope everybody's doing well. That's the end of stats. We're done. All you have now is the final. So everybody, get your questions into me. Let's make sure that you are well prepared to complete this final. And I just wish all of you the best of luck. And hopefully I'll get to see a few of you today at graduation again. Everybody take care, and I'll be talking to you soon.